Hello, good morning. I'll get started right now. Okay. Last week, I believe that everybody has turned in the homework already, and everybody are doing quite a good job. So I'm quite happy about that. And I actually assembled a whole set of the GCD programs and send out to everybody. If some of you did not receive it, let me know. The purpose why I send out this set is because number one, this is for your own records, and you know that you have done this, and also can share everybody's idea about how to implement a GCD. And in fact, GCD algorithm has quite many different kind of way to do it. And myself include my own version on a recursive version, and I try to minimize it within 2-3 lines of code. So, and it also showed that Python language is very robust, and you can write a very small size of code to complete something that you need a lot of code in other language. And in fact, some people can do a single quick solve in one line. So Python is quite a good language for doing that. But in other way, Python is very confusing as well because it doesn't have the data type declaration. So it has some of its drawback. And performance-wise, it is slower than Java and also slower than C language, but it is easier for students to pick up as the first language. So right now, about 30% of the university are using Python as the first language in their college course, computer science 101 type of course. And then Java still quite popular, maybe taking about another 30% of it. And the rest of the school, some of the school, especially the engineering type of school, are using C, C++, but that percentage could be somewhere around 10%. And the purpose of having this package is we have the discussion board on which programming language that you prefer, and sending out such a package, you will be able to compare the different language that other people use. And in fact, we have the majority of the people using either Java or Python. And I actually did not include a C program because I forget to download it, and I'm sorry for that. But one of our students, or two, maybe two, have used C language to do that. And that's, but I have a discussion with Professor Crum and about current situation of the C language in school. But he told me that currently the percentage for using C language in universities are not very high because a lot of people are using Python or Java because of the simplicity. But in fact, C language in industry still has a lot of opportunity, especially on the more toward the hardware side or system side. That actually still have a lot of job. Okay, so that's my report on the programming language. And early this week, for the first session, I introduced the tool, the Flex tool for lexical analysis for scanning stage. And in this session, I would like to focus more on the Bison that is YACC, YACC, yet another compiler. So that is a software that is working with Flex for the automatic compiler design. And this session we will start to look at it. But the Bison or YACC and the Flex would need quite many tutorials. So along the way, when we continue our chapter 2, 3, 4, and 5, you may continue to see different lab. But because I developed this course starting in last December, but the first day I pulled my program onto the Blackboard system is on January 29th, and the due date for me to submit the course is February 28th. So effectively, I have about 1 month of the time to do that. So some of the material still not complete yet. So I'm trying to upload more things on the Blackboard system, and so you will continue to see some of the module continue to pop up, and that's I'm continue to improve the system. So right here, I would like to show you some module that I actually included this week. The first thing I would like to show is on week 2. This week, I actually include this part, the Bison bug fix. Okay, and some of you may have installed the Bison and Flex. I believe that upper here I have one installation guide for Bison and Flex, and you should have already installed it. But before you install the Flex and Bison, you need to implement install the code block for C and C++. And after that, you install this Flex and Bison. But somehow the current version that we are using, the 2.4.1, has some bug, and you need to look at this video for a patch. But it is not hard to patch it. Basically, here we have one download link. I already included the patch over here, so you just click this patch, and when you download, you will see a bison.exe file. You just copy the file over to the program file location 32-bit, the x86 directly, and then find the Bison executable file and just paste it and replace it. That's all you need to do. And right here on this page, there is a SourceForge page regarding GNU window, and right here number 473 Bison 2.4.1. there's an error report right here, and pull down, and right here there is one anonymous person who contributed this Bison binary patch. So that's what I use, and with this patch the whole thing will work perfectly. So, and other than that, you will see some of the practice Flex and Bison. And right here, I only have the PowerPoint file. For example, I click this one. That's an overview of Flex and Bison. And today, I'm going to teach some of these. So you will be able to download a PDF file, but so far I have not done the video file yet. So you probably need to study this and download a PDF for your own reference. And here we have 4 tutorials. So effectively, in the long run, I need to create 4 videos, but so far I don't have the time to do that. But today we will cover some of these. Sorry, it's a little bit hot. I'll take off my jacket. Okay, now we are going back to chapter 2. The reason why I want to include more of the discussion on the Bison tool and Flex tool is because the textbook, this programming language programmatic, is quite a good book. But if you read it, you will find out that this book is very theoretical and actually not easy to swallow at all. And they have a lot. This book has a lot of content, but actually, it's very theoretical and very hard to do to read. And also, after reading it, you probably don't know what's the use for this kind of knowledge. And so I try to have our discussion on the lex and yes and the regular expression in chapter 2, 3, 4, and maybe also 5 to show you that we actually can use the knowledge that we learned from the book and also put them into use for real world problem solving, not only the compiler design, but also many real world problem solving applications. And the previous lecture, the previous session, we had already seen the power of the regular expression. And in this week, I will continue to introduce the, I'll continue to provide you the tutorial on the Flex and Bison. And now let's get started chapter 2 on the parser part. So let's jump to the parser part. Now we are going to start the discussion on the parsing, but right here we will start to discuss the general idea. After the presentation of the general idea about parsing, I will start to talk about the lex and flex, lex and yes system. And after the discussion for lex and yes, we will come back to LL parsing and LR parsing. But this session probably I calculate maybe we can only finish the LL parsing, but not the LR parsing. So maybe tomorrow morning we need to continue on the LR parsing and the rest of the chapter. So let's get started on the parsing. First, we need to know parser is the core for the compiler. So basically, if you look at the natural language, when we try to analyze a language like English or Spanish, we basically rely on the grammar. And parser is analyzing the language by using the syntax. So it's syntax analysis. So effectively, it's like a grammar checker. And you can use the grammar checker to check the validity of the language or some speech or some article. And also, you can use the parser to translate from one language to the other language using the structure of the language to do the translation. For example, if we have English, say, I say, I love you, you have a subject and verb, and the verb is love, and you is the object, right? But this, you have a subject, verb, object structure. And then if we look at, if we study Japanese, for example, it's you need to say watashi wa anata o suki desu. Watashi is myself, and anata o is you, and then suki desu is like or love. So basically, the structure is different. It is subject, object, and then verb. So you need to use the structural difference to do translation. And that is why after parser, we decorate it with value, you generate the intermediate form for code generation. So this part is actually the crucial part. And the front end, including the lexical analyzer and the syntactic analyzer parser. And the lexical analyzer part is actually just garbage in, garbage out. You have the character and you have token coming out. So basically, you do not change the order of the characters. You just group them together into tokens. And parser will ask for the input from the lexical analyzer or the flex or lex part. And parser not only do the job, or also it will provide a semantic error or syntax error to report to the programmer. Okay. So parser is the heart for a typical compiler, and in parser you will build symbol table, syntax tree, and doing semantic analysis. So parser calls a scanner to obtain the token of the input program, assemble the tokens together into syntax tree. So you are trying to use token to build a syntax tree according to the grammar we provide, the CFG, the content-free grammar, or Baker's norm form, BNF, and pass the tree to the later phases of the compiler, which performs semantic analysis. And in fact, the semantic analysis still in parser. You can, it is part of the front-end compiler. And then you would translate, after the semantic analysis, you would create a decorated tree, syntax tree. And then you can generate an intermediate call or bytecode, or sometimes it is assembly call. After that, you do code optimization and for code generation. So effectively, parser in charge of the entire compilation process. And this style of compilation is sometimes referred to as syntax directed translation. And right here, we have such a diagram. This one is adding the semantic analysis in there, but you can group them together from parser to the end of the semantic graph. We can call this as parser. But if we only look at the grammatical structure or the syntax structure, we actually create an abstract syntax tree. But semantic analysis adds some value evaluation over this AST and create something called semantic graph. And in fact, this is a tree, but because of the backward linking, it becomes a graph. So we call it semantic graph. So semantic graph is actually AST is a tree with additional property and result references. And the reference can go back and become a loop or two-way tree. So we call it a semantic graph. And right here is a LR parser. And the reason why we present this LR parser is it is a typical structure for a table-driven parser. So we have the parse table, and we have the parser loop or the driver program. So this one is similar to the lexical analyzer that is table-driven one. And we will use the parse stack and value stack to store the tokens. and in a stack. And by push and pop operation on the parse stack, we will be able to build up a tree like this, because tree usually is suitable for push and pop of the stack. And especially you have the binary tree, it's easier to perform the push and pop. And in fact, the stack is the postfix structure. And postfix, actually, we basically convert a infix token string into a postfix stack, and then use that stack to convert to a tree. That's the whole idea about using stack. And parse stack and value stack are of the same order, so that's not hard to understand. Terminology. Context-free grammar, we will use this term quite often, and it is equivalent to push-down automata. And we also would have the terminology for simple. You will hear terminal, that's tokens, and non-terminal, that is actually some production rules left-hand side, and you can use to derive some right-hand side value and go into deeper evaluation. And we have production or production rule or grammar rule, and then we have derivations. And derivation has leftmost and rightmost or canonical, and this is the this will be the derivation direction. So this leftmost is LL type and rightmost is LR type, and we have parse tree and sentential form. And now let's look at the sentential form definition. Sentential form, mathematically, we define as a sentential form is the start symbol S of a grammar or any string that has a vertex or non-terminal union with terminal, 0 or more repetition. And what does this mean? Actually, this is hard to understand. And that can be derived from S. So S can derive into a combination of the vertex or non-terminal and terminal in union for several times. So consider the linear grammar. We have initial state S and another state or another non-terminal B. So this part is the vertex. And this part A and B are the terminals, and S is the starting symbol. And then this is the Q part, the state transition part. You can have these four rules: S to go to A and S go to B, and B go to B. B is lowercase b is terminal, uppercase B is a new non-terminal, and B to lambda. Lambda right here is actually means the empty string. And a derivation using this grammar might look like this: S, A, S, A, B, and then A, B, B. So starting from S, you apply the first rule, you become A, S, and then the S replaced by B, it become A, B, and then B replaced by B, B, it become A, B, B, and then this B replaced by B, B again, you become A, B, B, and then eventually you have this B equals empty string, so you got a resolve ID of the ABB. Anyway, each of these, anything in this linear derivation, the grammar is linear, anything in here is called, each of these is a sentential form. So, and what does this mean? This actually means, I will use a very simple example to say this is something as long as you follow certain grammar, So today, for example, I would like to say something like, I am happy. I am happy to go to school. I am happy to go to school to study math. I am happy to go to school to study math for the coming exam. So something like that. Everything in that combination, as long as it follow a certain grammar set, any of that is a sentential form. So it's a sentence type of form. So by the example I just mentioned about, it's not hard to understand why this is called a sentential form. Parsing, by analogy to a regular expression and DFA, a context-free grammar, CFG, is a generator for a context-free language. So context-free grammar, so the grammar is the input part, the rule definition part, and we use a finite state machine to check out the language. So actually, this is a generator for the language, not hard to understand. And a parser is a language recognizer of NQ. This is BO notation NQ, because you have the number of the input string, that's N. You have the number of the states, that's another order of N. More input string, you have more state, and the other one is the next the next state. So by doing that, your loop actually have the number of string coming in, and you have the second order loop, two nested loop. So that become an order of n cube. That's not how to understand why this language, this algorithm is n cube. But n cube is intractable by the computation theory. For trackable problem, we want it to be n log n. Under or matching n log n time, we call it trackable. N square or n cube are considered intractable program, so that will grow and become unmanageable. So there is an infinite number of grammar for every context-free language. Not all grammar are created equal. However, they are large classes of grammar for which that we can build parser that run in linear type. So basically, we are trying to find a set of grammar that can perform much faster. So that's why this textbook is spending a lot of time explaining the LL1 grammar, LR1 grammar, the LR0 grammar, the LALR grammar, or SLR grammar. The different classes of grammar actually perform in different time complexity. And we try to find a good parser that run fast. That's the whole purpose of studying these different kind of grammar. The purpose is to find something that work and actually work efficiently. So parsing is order n cube time. That's and they are two well-known algorithms. The early algorithm and Cook Younger and Kasami algorithm, the CYK algorithm. Anyway, that's all too slow. Now, let's look at parser style. And parser style, depending on the grammar family. So as I mentioned, its efficiency depends very much on the grammar's design. So we have two main class of the grammar, the LL grammar and LR family grammar. And LL stands for left to right. So you start reading from token by token and right and leftmost deviation. So we use the grammar rule from left. That is called LL grammar. And L, you have the big one on bottom. So you actually, it's kind of top-down shape for LL family. And LR stands for L left to right, rightmost derivation. So you start to apply the grammar rule from the rightmost part. So it's a reverse order, so it's like bottom up. This I just help you to remember whether it's bottom up or top down. So reverse means bottom up is the reverse way. So LL family left to right, leftmost derivation, and then parsing is top down. Algorithm is predictive. Why it's predictive is because you have not seen all of the token in the string yet, so you have to guess which rule it can be applied. And the LR derivation, actually you're starting from the bottom, and why we can evaluate from the bottom is because, and from the right, is because that we push the tokens into a stack, and then we reduce the rule, we pop them up and reduce. So this is so-called a shift reduce format, and that actually had already seen all the token already. And since the push and pop operation for all the token is in linear time, so actually shift the push and pop operation did not actually does not actually add time complexity into the algorithm, because we know that the parser algorithm is order of n cube time complexity. So something that is linear time, no matter how many you add into there, actually doesn't hurt too much. So that actually, because you have dominating factor of n cube over there. And parsing, LL parsers are also called top-down or predictive parser. LR parsers are called bottom-up or shift-reduced parsers. And there are several important subclasses of LR parser. So LR parser receive more study. You have the SLR, the simple LR parser. That is a bottom-up shift-reduced parser with small parse tables and relative simple parser generators algorithm. And we will explain why later. And this is quite a popular parser algorithm. And the next one is something a little bit bigger than SLR parser. That's look ahead LR parser. And look ahead LR parser is a simplified version of the canonical LR parser. We will see some definition later as well. Top-down and the bottom-up parsing. Consider the following grammar for a comma separated list of identifier, and the production can be parsed top-down by top-down or bottom-up parsers, and we will explain this later with real example. So basically, this is a list of ID, comma, ID, comma, ID, comma, something like that. We will see the difference. First one, we would like to look at the top-down LL parser. So basically, we have these three rule, and it is a top-down parser. So actually, right here, the top-down parser begin by predicting the root of the tree, the ID list. So ID list is the root of the tree. Starting from here, we apply this rule. So it will apply the first rule by taking this ID and the ID list tail. And then the parser then move down into the first non-terminal child. The first non-terminal child is this one. And then replace by ID and ID list tail. And to make prediction, it need to pick at the upcoming token a comma. So when you see a comma, then we know we need to apply the second rule. So you see a comma, we apply the second rule. So it should be a ID, comma, ID, and then another ID list tail. It then match the comma and the ID and move down to the next ID list tail. So we will move down to here. But if right here you don't see an ID, then you will report the error. So in a similar recursive fashion, the top-down parser walk down the tree left to right, predicting and expanding the node and tracing out the leftmost derivation of the fringe of the tree. So eventually we will finish this A, comma, B, comma, C, and then semicolon. We will pass this kind of token string into a LL syntax tree. And the bottom up part, you actually starting from bottom. So actually you have the you look at first ID and push into the pass tree, and then comma, and then B, and then comma, and C. After that, you've seen everything already. You start to do the derivation from the right. So from the right, we actually see a this semicolon. So let me go back to the previous page. In the semicolon, we know that that's a ID list tail. So that's using this third rule. And then you find it is a ID list tail. And when there's an ID list tail, we know that it is by the second rule, the right-hand side of the second rule. By the right-hand side of the second rule, we know that these three in combine will have a left-hand side over here. And when this left-hand side show up, actually, you further combine the comma and the B and then comma, and then you find out the ID list tail again. And after that, you actually check the first rule, you will find out it will be an ID list with ID and ID list tail. So this is pushed in all of the tokens, and then you pop out the top one, starting to do the reducing. So this part is shifting, push in everything, and this part start to do reduce, to pop out things. That is called the reduce part. Canonical derivation. At no point does the bottom-up parser predict what it will see next. Rather, it shifts token into its forest until it recognizes the right-hand side. When the right-hand side finishes, then it starts to reduce to a left-hand side. And then that left-hand side will be part of another rule's right-hand side. And then you start to move up the tree. Because of this behavior, bottom-up parser are sometimes called shift-reduce parser. Moving up the figure from bottom to top, we can see that the shift-reduce parser traces out a rightmost derivation in reverse, so from bottom up. So that's why I use the R as reverse. Because bottom-up parser were the first to receive careful formal study, rightmost derivation are sometimes called canonical. So because it's like typical or classic parser. And here we have bounding space with bottom-up grammar. And because the previous grammar, you need to actually push a lot, have many push operation and have many pop operations. So we can further optimize the grammar into this bounding space grammar. And the idea is instead of having ID, comma, now you push in the first the first ID, and then combine with comma ID, comma ID, comma ID. So, and at the end, you will have a ID. You will have, by this second rule, you will have ID, comma, that will be the end of the, that will be the right hand side. The rightmost part will be a ID, comma, okay, because this ID is part of the ID list prefix. So if there's only single ID, that would only be a ID. And if there are multiple, has an ID and comma, this ID list prefix should be ending with comma ID. And then because it's recursive, so every ID list prefix will end with ID, comma, ID on the right and comma on the left, something like that. Until the first one, you have ID only. So right here, we pass the A, comma, B, comma, C, comma again by using this duo. First, we have we see a ID, then we actually know that this is a ID list prefix because we apply this duo. And then we see a comma. When we see a comma, then we know that this ID belongs to this ID list prefix, and we are expecting another ID after the comma, so we get it. After that, we know that this is a ID prefix, and then combined with another duo of comma ID and ID list prefix format. And then we see another comma, and then we see another ID. We build up another level. And then at the end, we see a semicolon. We finish the ID list. So this is called a bounding space with a button-up grammar. And this type of parsing cannot be used for LL parsing. So actually, this is more button-up algorithm. But as we can see, that one is more efficient than the simple LR parsing. And every LL1 grammar is also a LR1 grammar. Right here, LL means the left to right, leftmost derivation, and the number over here is the degree of look ahead. How many tokens we look ahead? We put a 1 over here. So LL1, whatever grammar that can be parsed using the left derivation can also be parsed by right deviation. So this LR1 is bigger than LL1. Though the right recursion is production, the right recursion in production tend to require a very deep stacks and complicated semantic analysis. But we know that LL1 is a subset for LR1. Every CFL that can be parsed deterministically has a SLR1 grammar with it. So basically, if the CFL have no confusion, you can determine by looking at the tokens. Then we call it a SLR1 algorithm. So that actually can bring down the execution time for the parsing by a lot. And every deterministic CFL with the prefix property has a LR0 grammar. And LR0 grammar is actually even faster than SLR1 because there is no look ahead. But there is only quite limited grammar can be classified as LR1. And that one is with the prefix property. So prefix means you can predict by some rule like this. That is the LR0 type grammar, and it will be faster because this is actually very similar to top-down, but actually it just, if you look at it, it just actually look at 1 token, 2 tokens, 3 tokens, keep on reading 1 more token, and after all the token being read in, you finish the parsing already. So this is actually close to linear time. So this is the fastest, but with the least expressive power. The set is the smallest. And parsing, LR parser with one token look ahead. You commonly see LL and LR with some number written with a number in the parentheses after it. The number indicates how many tokens of look ahead are required in order to parse. Almost all real compiler use one token of look ahead. So the LR0 actually is only used for some simple, very simple language. And real world compiler need to have at least one token look ahead. The expression grammar with precedence and associativity you saw before is LR1, but not LL1. And we will talk about why it is not LL1. Expression for arithmetic, example 2.8, not covered here, we'll show it later. So the expression grammar you saw is LR1. So let's look at the example 2.8. And example 2.8 right here, this one is a LR1 grammar because right here you have a turn, and this one turn on the leftmost turn. On the right hand side, it actually has the left recursion. With left recursion, it will not be a LL grammar because it will not support the recursive descent algorithm. So that's what this actually said. The expression grammar is LR1, not LL1. So the type of parsing, you have the LL type and LR type. You have top down and bottom up. And bottom up, you use the shift reduce algorithm, and you have the typical LR0, LR1, LR2 different parser. And you also have the SLR, that's the simpler version, and LALR, that's look ahead LR. And in fact, there are several different type of names, but we just have such a classification right here. And top-down parsing, you use a recursive descent algorithm. You will need backtracking or non-backtracking algorithm. For non-backtracking algorithm, you will need to have predictive parser. And this predictive parser is very tedious. In the LL parser lecture, we will talk about this predictive parser, and that is LL parser. General case for LL parser, you have LL1, LL2, something like that, a whole family. And backtracking usually used for simpler case. Parsing 3, recursive descent parsing. So now we are going to look at the LL parsing using the recursive descent parsing. So right here we have the calculator grammar that we used last week, not last week, Tuesday for our next example. And now we have top-down predictive parsing. And the calculator allows the value to be read into name or numeric variable, which is used in the expressions. Calculator allow value to be read into there. And then expression return to the output. So you have the read in statement. You also have the write out. That's what it said. And the control flow is linear, no loop, if statement, or jump. So basically, this language only supports the linear operations, no loop, if, or jump. So no structural operations. The end mark pseudo token is produced by the scanner. So at the beginning of the evaluation, this $$ will be inserted at the end of the first dual, and that actually is the bottom. It's the bottom of the stack. You will have this double dollar sign over there. So when you see this token, that means the parser will finish the whole program. As in regular expression, we use the symbol epsilon to denote the empty string. A production with epsilon on the right-hand side is sometimes called a epsilon production. So right here, we have this one is a epsilon production rule. This term tail is also a epsilon production rule, also for factor tail. Recursive descent algorithm. So we know that this is a LR algorithm, so it's not suitable for recursive descent. So it is helpful to compare the expression portion of the figure 2.16 to the expression grammar 2.8. LR grammar is significantly more intuitive. It says this one is more intuitive. So basically, the word is said intuitive is basically you can, when you write down a mathematical term, you can read it right away. An expression either is a expression, a term, and the term can be a factor, and the factor can be an ID, so it can be a variable or something, or it can be something add something or something multiply something. So actually, this is called an expression. So intuitive means easier to read, and this LL grammar on this 2.16 actually not as readable. You have the statement list, you have the term tail, you have factor tail. So those kind of extra non-terminals make it not as readable. So it solves a problem. The LR grammar solves a problem similar to that of the ID list grammar. If we see an ID on the input, we expecting an expression. We have no way to tell which of the two possible production will be predicted. So basically, you will have the confusion because the single term, you don't know which one it is. And grammar in figure 2.16 avoid the problem. So it had already terminated the deprecation part. I'm sorry, the confusion part, the ambiguous part. So that's what it is. In effect, we have sacrificed grammatical elegance. So we make things not as readable to achieve the LL grammar to allow the recursive descent algorithm. And now we would like to look at what is recursive descent parsing. So we talk about this term, but we actually don't know what it is. So it is a top-down parser. It builds from a set of mutual recursive procedure. So they are a set of mutual recursive. Somebody can call, some function can call another function, and another function can call it. It's called a mutual recursive procedure. And the structure of the resulting program closely mirror the grammar it recognizes. So the target syntax tree is something like this. We have 5 terminal and 4 non-terminal points in this tree. And the parse tree is constructed from the top, from left to right, and backtracking. Backtracking means that when something mismatch happen, you will backtrack. And we will show this later. And terminal are seen in the order of appearance. So basically, you have the input string like this. The whole algorithm is trying to take in such input string and generate the syntax tree like this. And now let's look at how it can be achieved. And right here, we are considered such a very simple algorithm. Basically, you have an expression, And expression can be a term or a term plus expression. So basically, you can think about this can be a variable A, and this can be a variable A plus parenthesis B plus C or something like that. And then this term, in turn, it can be an integer or some integer times a term. And the term can be recursive to be another integer or something. Or this term can be an expression with parentheses. So put down here, the term can be A plus B parentheses plus expression that is actually another term. And you can put another term in with another parenthesis in there, something like that. You can construct a more complicated expression. So the token string that we will process is very simple. It's left parenthesis, integer, and then right parenthesis. So we start with the top level non-terminal expression and try the rule E. We're starting with the E in order. So we started with the expression. Now we're starting to read the token in. The first one we see is a parenthesis. And parenthesis, we saw a parenthesis, then we try to determine it can be the term or term with expression. So let's try term first. So let's try term first. And then this term actually go to integer, but we still with the left parenthesis at this point. So this term will go to evaluate. First one is integer, and apparently it's a parenthesis, so it's not integer. So this actually is a mismatch. So we need to backtrack. So we take out of this integer, and then we try the second term because we try term and then this doesn't happen. We try the second one. Second one should have integer, star, and then term. And this is a left parenthesis. So again, mismatch. So we need to clean all of this, go back to term. So we go back to term, we should try the third rule. That's the parenthesis, expression, and then parenthesis. So this one actually, okay, it is a left parenthesis, so it matches. So when it matches, we will go down to this because these have been used. So now we will predicting there is some expression there. So now we move the token to the second one, and the second one we try to evaluate the expression. So actually, if expression will evaluate to term and term go to integer, so it match. So this one match. So this one match will advance our token. So our token will be, okay, this expression evaluate term and then evaluate to this integer and it match. And then we will move token to the right parenthesis. And we check with this and it match. So actually this is the end syntax tree we will get. So actually this is the end of the input. So the whole idea is we have the input string, then we actually read into some memory and we do lexical analysis. So we actually group them into tokens. And now we start to build a syntax tree by syntax analysis. So first, this is a certain keyword, so we actually would note it. Then we try to evaluate this part. So we actually build a parse tree like this for this a greater than max. And then we try to evaluate this max equals a part. And eventually we build up a complete syntax tree like this. Okay, backtracking. When a syntax function fails, we want it to have no side effect. We want the input to be exactly the way it was before calling the function, because this makes it easier for other functions to have a go at passing the same input. So basically, we need to clean out whatever we have and then try other function. In addition, the function should delete any object it created, remove any symbol it entered into the symbol table. So basically, restore the whole condition back to the situation that without going into that production rule, we try different rule. So in other words, the function had to backtrack to earlier situation. So now let's look at how to build a recursive descent parser. So building a recursive descent parser, we can formalize this process in one of the two ways. So basically, this two way is recursive descent that we introduced already, and the other option is to build it as table driven. And in this lecture, we will be focused on this recursive descent algorithm. So basically, a parser architecture will be like this, and we will look at this predictive parser that I talked about for the LL family. But right here, we are talking about recursive procedure that's not table driven. So in this lecture, we are talking about the recursive procedure, and we will have another lecture on the table driven using the prediction rules. Recursive descent parser for the calculator language. So we are talking about the figure 2.16, the calculator language. Pseudo call for a recursive descent parser for our calculator language appear in figure 2.7. 2.7 is on the next page. Okay, so this is 2.17. And it has a subroutine for every non-terminal in the grammar. It also has a mechanism input token to inspect the next token available from the scanner, and a subroutine to match to consume and update the token. And in the process, verify that it is the one that was expected. So basically, this just say that we will follow the recursive descent algorithm to check the grammar, and a match or any of the other subroutines see an unexpected token, then the syntax tree error will have occurred. For the time being, let's assume that the parser error subroutine simply print out a message and terminate the parse. So that actually, in this version, do not handle much of the error handling. And in section 2.3.5, we will consider how to recover such errors and continue to pass the remainder of the input. So that's backtracking. So let's look at the algorithm. It's easier to understand. So basically, the main program is right here, and we have a subroutine or procedure called match. And match, you put in a certain expected symbol, and if the input token is equal to the expected symbol, then we determine that is the right token we expect. So we consume that input token. So that's the function of the match. If not, if we read in the wrong token and other match, then it is a parse error. So right here, the program, we started from program. So every rule right here has a corresponding subroutine. So when we have this first rule, we have the program and then the program actually take in the first token, and the first token will have to be ID read or write. What's this rule? Let's look at it. Let me try to find it. Okay, right here. So basically, the program start with the program will have a leading token of ID read or write. So that's what the duo, the function is checking right now. So let's go back. So right here, when your program start, the first token that can only be ID read or write. And these are different rules because program will expand to statement list. Statement list will expand to term. So statement will expand to list, and this will have 3 possible leading or first tokens. So these are the 3 only possible token. Another one is this $sign, double $sign. That's the end of the program. So we would evaluate statement list and then evaluate matching of the double $sign. So this actually is these 2 function call, and then we will evaluate the statement list and go to the second rule. And the second rule, we take in another token. Again, right here, the possible leading tokens still be ID read and write. And then ID read and write, in that case, it can be a statement followed by a statement list. So we evaluate the statement, we go to here, and then we will try to match ID or match read or match write. If this input token is ID, we try to match ID, and then we try to match the assignment, and then we call the expression. So this part of the rule. And if the input token is read, then we try to match read, whether read is in or not. If not, then we'll report parser error. If yes, we try to match ID, whether it's an ID or not. And the third rule is this one. Otherwise, we'll report parse error. So basically, every single rule we see right here would have a subroutine actually matching it. So that's the way we call it a recursive procedure for each terminal. So right here, it said that it has a subroutine for every non-terminal in the grammar. And then the terminal one, we use the match function to match it. So recursive descent parser is actually quite simple. The non-terminal, you use a subroutine. Terminal, you use the match function. That's it. And if there is no match, you report error. The rule is quite simple, so you just try to implement every single procedure for each rule. LL parsing, like the bottom-up parsing, bottom-up grammar, this one captures associativity and precedence. But most people don't find it as pretty. For one thing, the operand of a given operator on in right-hand side together. So, and however, the simplicity of the parsing algorithm make up this weakness. So basically, that recursive descent algorithm is very easy to implement because you just need to use the simple rule I just mentioned about. The rule, you use a subroutine for non-terminal, and then you try to match all of the terminal one and report error when it happened. The rule is very simple, but sometimes the operand may not be there. But we try to avoid problem and try to make sure the parsing work and actually building some heuristic. Sometimes you can make this LL parsing to be quite efficient with the recursive descent algorithm. And right here is one example, average program, read in A, read in B, and sum average. And this example will be used later for the prediction table, table-driven method. So we will see this later with the prediction table later. And that average program by recursive descent will be built like this. We won't go into detail right here, but the sum average we will have chance to study it later. Now we finished the general parsing already. Let me check our friend. How are they doing right now? So right here. Okay, we still have two people. I don't know whether they have question or not. Okay. Then the next thing I'm going to do will be more interesting. And right here, I have attached the Bison bug fix in the website. Now we will look at our Flex and Bison part. Because we have already had the general idea of what parser is and also different class of the parser and why we need to study so many parser because we want to find a very efficient one. And that's enough. And after this Flex and Bison discussion, we will return to our textbook on the LL parsing, LR parsing to study more detail about those parsing. But we don't need it right now. What we need to look at right now is how parser work and how parser can solve our problem and how can I design a parser and how can I have parser working with my lexical analyzer to solve real world problems. So that's what we are looking at right now. And with that, we will know better about different classes of the parsers. We can have a better idea of why we choose such a parser. If we don't know the purpose of the parsing and compiler, then we have no way of judging which compiler would be better. And by choosing the compiler, actually, we also choosing the language. For example, if we choose interpreter, then we choose maybe Python. If we choose hybrid type of the parser or compiler, we pretty much choosing Java or C#. And if we want to have the compiler to compile to machine code, then maybe we are choosing C or C++. So that's why understanding our purpose of using the parser and the lexical analyzer is very important. So let's look at the overview for Flex and Bison. And the last week, the part 2 of the first week, we talked about regular expression. And early this week, we talk about using the Flex or lexical analyzer as an independent program. But right here, we start to use the lexical analyzer together with Bison. And in fact, using the Bison to drive the Flex. So the methodology is quite different from the session 1. That example is good by itself. It's only used to analyze doing the lexical analyzer. So some overview for Lex and Yet. Sorry. Before 1975, writing a compiler was a very time-consuming process. In 1975, I'm about 8 years old on that year. Then these two gentlemen published paper on Lex and Yet. This utility greatly simplified compiler writing. So at all time, they all call Lex and Yet. That's 1975. This utility greatly simplified the compiler writing. Implementation detail for Lex and Yet may be found in such document. Anyway, we have a listing later. Flex and Bison are clones for Lex and Yet. So Flex is a clone for Lex, Bison is a Yet, and both of them improve from Lex and Yet. So the grammar has slightly different, but the majority of the grammar is actually similar for Lex and Flex, Lex and Flex, and Bison and Yet. So you can obtain those free from GNU and this CYG Sigwin. And Sigwin is a 32-bit Windows port of GNU software. So it's a whole collection of software from GNU. In fact, Sigwin is a port of the Unix operation system to Windows. So you pretty much try to port all the Unix system onto Windows. So they actually is also certain shell you can mimic the Linux or Unix on Windows. So that whole set comes with compiler GCC, G++. To install, simply download and run the setup executable. So we have a simple way of doing that using the code block. And the code block comes with GCC. And then the default install Bison Flex. And we have the separate Bison and Flex installation. So that's done. An editor, we don't need this VIM. VIM is very old-fashioned editor, so we don't need that. And this can be found in the environment. Okay, let's move on. So right here, I show you the format. So we have a source code with such statement. And this statement, after lexical analyzer, you will create tokens. So you become something like this. And then we use context-free grammar to generate a syntax tree like this. And then we do code generation. And Flex is for the generation of this lexical analyzer. Yet is used to do syntax analysis, and sometimes you can also use for code generation. We will explain it later. So lexical analyzer Flex, actually it will take in the input format of Lex file in .l format. The lexical analyzer matches string in the input based on your patterns and convert the string into tokens. Tokens are numerical representation of string. These are simple. When the lexical analyzer file is identifier in the input string, you enter them into symbol table. So this actually just saying that you read in the token and put it into the symbol table. These are easy. And subsequent references to the identifier have to find a symbol table. So anyway, you build up a symbol table by using the tokenizer, the lex.yy.c program, and then you actually use that symbol table for everyone else. That's the whole thing right here. And then the next one, syntax analysis and semantic analysis. You basically get in a file in YAC format. It's .y file, Y for YAC. And then that's actually written primarily with context-free grammar. We'll see it later. The syntax analyzer uses the grammar rule that allow it to analyze token from the lexical analyzer to create syntax tree. So this is just talking about the figure we just saw. And then, for example, operator precedence associativity are apparent in the syntax tree. Something like that, you need to follow the rules. So basically, this just repeat the statement that we saw on this figure, the function of Lex and Ex. Now, I will introduce how Bison and Flex work. So first thing, you need to have a file called calculator.y. This is the definition of the EX format grammar file for calculator language. Calculator language, I show, make the name short as CALC. This is for the simple calculator program. And that EX file will be sent into Bison or EX. And then if you choose Bison-D and then calculator.y, you will be able to generate a table header file as calculator.tab.h and a C file called calculator.tab.c, y.tab.c. Okay, let me stop here. I have to check our friend. Are they okay with the header file? Because I know that only probably two or three of you has better experience about C language. And I don't know whether you know about header file or not. A simple way to understand the header file is actually, I don't know whether you know about, okay, you are okay with the header file. Okay, then I don't need to worry about it. If they have problem, I will try to explain it. Okay. A very simple way to understand the header file is if you know about the Java program, and Java program has interface, and interface only have the abstract method, and abstract method only has the signature but no body. And those type of interface or abstract class that actually is working just like a header file. It has the signature of certain function. So in C language, that's the all-time definition of the all-time language. And in order to share the resource in a C file, we actually build some header file, and usually the header file including the header of a function or the signature part in Java's terminology, and also the macros or constants put into the header file for other program to share. So basically, to be short, we have the Y file, that's the EX format for the grammar definition of the calculator language, and we generate the calculator parser program in calculator.tab.c. And then we also create a calculator.tab.h file, that's the header file for the tokens. And that token information will be used as the token definition. If you see the previous lectures file, that we use a series of define and the token number and token name and token number, that scanner.h file is similar to this calculator.tab.h. And we feed this .h file from the grammar rule into the Flex. So Flex actually is driven by Bison. And then we use that token definition file with the calculator L, the regular expression definition for each token. Use these two information to generate the tokenizer or the YYLex function to generate the tokens from the input file. So these two in combine, we use the compiler -O to generate the calculator executable. So basically, these two, one parser, one the tokenizer, putting together to create the calculator compiler, or sometimes is actually a interpreter. And in today's one example, we'll show you how to make a interpreter. And then your program in calculator language, after the execution file have been created, that is actually a compiler or interpreter, then you put your program into the calculator compiler, then it will create a executable program, or it will create a assembly program, and that assembly program can be fed into a simulator and provide output to the console. Or you can do statement by statement interpreting and also create the output to the console. So we will see one example later. The project building process is actually, you first need to put your EX file and with -D. Without -D, this table will not be created. The header file will not be created. That means you only create a parser, but not the lexical analyzer. In that case, the lexical analyzer or the tokenizer, you need to build by yours before separately. And then you also create a parser file in here, and you use this calculator.l, and this .l file need to include the header file created by this one. And then use this, you create the Lexer or the tokenizer program, and use that, you combine to create the calculator executable file. And project building process 2. Bison read in the grammar description in calculator.y generates a syntax analyzer parser that includes function YYPass function. This YYPass function actually is the parser. So the whole purpose of having the Bison to create the parser, the end result is this YYPass function, and YYPass function will be called by the main program to become the core of the compiler. So this -D, we talked about it already, and then the table will be fed into the generation of the lexical analyzer that give you the YYLex function. And these two functions, the YYPass will automatically call this YYLex function, and YYPass is the main function in our compiler, and it will be called by the main function. And these are the reference documents. Now let's move on to the second tutorial in this series. Second one is to talk about Lex. And let's start it. And right here we talk about the Lex, the usage of Lex. We will not talk about the theory. And regular expression file, actually we talk about this. We'll see table 1, and pattern matching example is also in table 2. We'll skip this. And one thing to take note of is there are only 2 characters that doesn't need the escape sequence. That one is a hyphen. I'm sorry, there are two operators that will need to have the escape sequence. One is dash, the other one is circumflex or cap. When used between two characters, the hyphen will represent a range of characters. So sometimes this minus sign need to have escape sequence by backslash. And same thing for this cap. And cap is used for the first character in a class or a class set for negation. And two patterns of the same thing. When two patterns both match the same string, the longest one win. If both matches are of the same size, then the first pattern matching will win. The first one written down in the rule file will win. So this gives you the tiebreaker. If two patterns match the same string, the longer one will win. And of the same length, the first one will win. So right here, let's look at the regular expression in Flex. So these are the same. These are the same with the regular expression, except this one. Double quote, you put something in here, it become a keyword. It become a keyword. And actually, effectively, if you put parentheses, this is actually also a grouping. So this actually is also kind of similar to this, but sometimes it's different. We in the regular expression for flex or next, we have different things. We have different definition for literal and keywords. And the C language escape sequence still work here. So backslash n still can be put inside this double quote. Character set, when you have the brackets, inside there will be a set. So it becomes a set or collection of the symbols. And right here is the regular expression. I believe this is the same with whatever we have in the regular expression discussion. So I won't repeat it. And this table gives you the different function and different data structure that you will often use in Lex environment. So YY will return the tokens, and tokens are integers. So these are simple, but this will be called very often by the parser. And then there are three important variables. One is called YY text. So when there is a match string, then a token will be returned. That return token will be returned by this YY text. But there are three variables. This YY text variable will be representing the string that being matched. For example, 3.14159, that is the current string. But when we return, it can be a number, and the numbers token code will be returned. But this matched string will be the 3.1415, something like that. And then the length of the string will be assigned to YY length. And its value, the real value, will be assigned to this YY val or YY value. And the data type for this YY value can be redefined. So sometimes it can be an integer, sometimes it can be a real number. It all depends on the data or the ID's data type. And YY wrap is a function to wrap up the functionality of the YY list. So when YYLex input string or input tokens, the characters or tokens all being generated, then the YYRep will be called to finish up the whole thing. And then it will return 1 if the whole process is done. If 0, that means it's not done. And there are two files, YY in and YY out, for the input and output to the YYLex. So YYLex will read in YY in's file. You can assign this, and then YYLex will read it. And YY out is the output provided by YYLex. So whatever you print out or copy out will be going to here that you can assign if you properly assign it. And right here we have 3 macro. The echo is just to write and match the string. Initial and begin are initial or start or switch a start condition. So these are rarely used. We won't discuss. Let's look at more definitions. And the structure is like this. You have part 1, that's definition. Part 2 is dual. Part 3 is user program. And we saw this definition in the previous lecture already. But right here, what I would like to say is the definition is just like the header for C language. You have the macros, you have external link, you have the functions, definition, something like that. Rule is the pattern with the action. So this part will be converted to the nested case or switch statements that we talk about, the ad hoc way of writing a lexical analyzer. And the last part will be user program or your main program. So that part is you can define how to connect this with the YYLex file, or you can put the main program in another file and play very lightly on this part 3. So double percentage sign is used to divide the sections. And we will provide an example of the shortest possible Lex file, something like that. And let's go. So right here, we'll look at a demo program. This demo program will be the shortest possible Flex file. So you basically, you take in the \n. This semicolon is a C semicolon. That means there is a statement, but do nothing statement. So nothing will be done. That is a wildcard character. It also done nothing. So this program actually doing nothing. And on the right-hand side, we have the flex1.l. This one will accept any wildcard letter, any letter or characters, and write it down. And we will talk about this echo later. And also we have \n that will be write out as well. So effectively, your input file will be printed out without any modification. So basically, this is just echoing your input to output. And YYWrap just return 1, means that when it finishes, it's done. And the main program will call the YYLex, and YYLex right here only print out the functions, print out the characters without returning any token. So there is no variable to accept the return value from YYLex. So let's move on. So the two pattern we specify in the simplest program are the \n and the dot wildcard. So that's simple. And the action will be a single C statement or multiple C statement. When it is multiple C statement, we put it into a brace, into a pair of braces. And anything not starting in column 1 is copied to generate a C file. Okay, this is easy. And the echo is defined as this. So basically, the echo we see in the program right here is actually just write out your text, that is the color match the text with this length, that's the buffer length, and then to the output file. And default, this one is console. So print out to the screen. So that's what it actually works. Just print out your match the string to the console. And right here show you how they work. So basically you have a calculator.l program, and this program actually YYLex will be reading in each of the token. So for example, if right now our token indicator index is pointing to this right, and then it will return the right type token index number and return this number to the parser, to the main program. And when the whole token being consumed, then the YY will be called to finish up the wrap up whole program. And when we are reading this YYLex to take in the token, basically this right string will be assigned to this YY text variable, and 5 will be assigned to YY length, and the current line number 1, 2, 3, 4, 5, the 5 will be assigned to YY line number, and the real value, say this value, there's no value by this token, but if it is this A or this 4, the real value will be passed to this YYL value, and the data type can be changed or be determined by this YYS type. And then when we provide the token back to the main program may actually use the YY_in as the input file for YYLex, or it can provide the output to the YY_out. And okay, now let's look at the demo program. The variable YY text is a pointer to the match string. YY length is to the length of the string. These are token we covered already. Okay. Now let's look at the demo program. So right here I have a directory Flex Bison, and there's a CDEF. And CDEF I already zip it and post it on our breadboard system, so you will be able to download it to run. First one, let's look at this CDEF. In CDEF, we will demo right now for this Flex 0 and 1. Let's go into there. And we have this Flex 0. Let's open it. Okay, so right here you can see that this Flex0.l is the simplest program. So let me use this right shift and right mouse key on this Flex0 directory and open command line here. So it will invoke a command line, the command line window. Right here, let's do dir, check the file available over here. Then we can do flex, and then flex0.l. That would use this syntax file to generate the next.yy.c. So go. And we cannot compile it because there is no main program, no any supporting things. So I just want to show you this flex0.l will work. That is the simplest Lex file. Okay. The next thing I would like to demo is this flex2. So let me open the flex2 file. I'm sorry, first one. I'm working on this first one. And for this first one, we will go up one level in our command line and cd flex 1 dir. We have the file over here. Now this flex 1 is actually the one we do echo. We'll print out all of the content from your input file. So now let's execute it. We have the flex and then flex 1.l. Sorry, I have a typo. And then we do gcc lex.yy.c ho flex 1. So flex 1 is the executable file. To run it, and then we do flex 1. And right now, it don't have the assignment for the input file, so I put flex 1.l. So I use this file as input as well. Then it got echo out. Now let's return to the slides. Now we are going to look at the flex2.l. If you don't like the YY wrap, you don't know what it is, and you don't know how it works, you don't want to run it, so you can put a percentage sign option, no YY wrap. Then you don't need to call it anymore. You don't need to write it anymore. And in this program, we have the YY line number defined in the part 1 definition. Part 1, we have the percentage sign with left bracket and percentage sign with right bracket. Inside here, you can put whatever C program you want to have over here. Usually, you put in some definition file or include your token definition file .h headers over here. And these two double percentage sign is the part 2. So part 2, you actually start with cap, and then you have multiple of the character of wildcard character, and then finish by a \n. What this means is actually you finish the whole line, and then if you match one line, then you increase the line number and you print out the match pattern. So basically, you print out the line number in 4-digit format, and then you have a tab in between the line number, and then you have a string. This string is the match pattern. Match pattern means that line you are using. Right here, I'm using the first 2 as example, as the input file. And right here in your C program, you have a parameter list. Int argument C is for count. So this one is the number of arguments. And character star V bracket. This one is array pointer. So basically, this is a string array pointer. I'm sorry, this is a string array. Okay, this is string array pointer, I'm sorry. And V is for vector. So when we have the argument V and then 1, the index 1 string, so basically this flex 2 is argument V0 and flex2.l, that's argument 1. Actually, this is the same when you have the main program in Java. You have the public static void main, and then string bracket and argument s, args, or you can even put argv over there. That's also legal, and that one actually will read in the argument array as well in the token format or string format. And this one, anyway, will take in a file name and open the file in read-only mode and assign the file handler to YYIN. And YYIN is used by YYDEX, excuse me, as the input file for processing the tokens. I'm sorry, the processing the pattern matches. And then when you finish the whole thing, you close the YYIN file. So let's look at the program. Excuse me. So right here, I move up a level. So in CDEV, let me open this Flex2 file. This Flex2 file is the same as we shown in the slides. So right here, I do the same thing, flex2.l. And then we do gcc, and then lex.yy.c-o flex2. And then we run flex2.l. And this actually is assigning this flex2.l as input file in read-only mode to the YYIN. So right here, I click, and then the line number is shown and the program being echoed out, and in between there is a text sign now visible. Let's return to the slides. Now we move on to the next one. Go to demo program 3. Demo program 3, we actually has the number count. And what this count is, there is a letter followed by parentheses, letter or digit. Letter or digit is alphanumerical characters. And then you have 0 or more repetition. So leading letter, lowercase or uppercase, followed by alphanumerical numbers. This is actually the ID format. So every time if there is an ID, we increase the count. That's what it is. So right here, we actually open the input file. In this case, it will be Flex3, this program. And then we count the number of ID in this file. So let's run it. So right here, I cd one level up, cd Flex3 dir, and right here, we go to Flex3, and let's open Flex3. And inside this Flex3, we have this. So now let's do it. So we have this flex3.l as input, and we have the number of identifier as 32. Now let's go to Flex5. And now right here, Let me move up to Flex 5. We will come back to Flex 4 later. But now let's look at Flex 5. Flex 5 is exactly the same with Flex 3, except that in the definition part, we have the digit, and then we assign with this regular expression 0 to 9, and later will be defined as A to Z lowercase or A to Z uppercase. So basically, by doing this, we actually specify a regular expression to a certain name, and this name later in part 2, we can use the braces and put later there. This will become the later. So actually, this is in the same structure as Flex 3, but it will simplify it because this can be used repeatedly. So right here, let's run it. We have the flex 5.l. And then we have gcc flex.yy.c -l, -o flex 5, and we run flex 5.l. Okay. Number of identifier increased by 2 because we have these 2 more things over here. So the index, the ID number had changed. Now we go back to see the number 4. The last one. This one, the flex 4. The flex 4 actually, if there is a \n, we increase the number of line, and \n also comes as a character, so we increase the number of characters as well. Then we would have anything in the character class, we have kept, then it will be inclusive list. So no space, no \t, no new line, and any character other than this will be acceptable. Then you have 1 or more, and that will increase the number of word count. What this means is actually this pattern is for any character block or any string or any token, that you will actually increase the number of words, and also your number of characters will increase by YY length. YY length is the match pattern's length, so it's the length of the string. It will be increased. And last, any other character, you increase the number of characters. So this file, flex4, is to count the number of characters or number of words and number of lines available in your input file. So let's run it. I'm sorry, I used the wrong flag. Should be -o. And similarly, I use this file as input. So number of character is 316. Number of word is 46, and number of line is 16. Okay, then that's okay. Then we finish this lecture. Now we are next. Let me see. Not this one. So we don't have time to go into the don't have time to go into the LL parsing anymore. I will finish this yet part and finish the talk today. We will have 2 more tiny lectures. So the first one is the yet application. I will introduce the Bison file structure right here. So in Bison file is similar. You have 3 sections. You have a definition, rule, and user program. And you can put into one file or multiple file. And I won't go into detail here. So the Bison file, your first part, you put a definition, and you have the .h file, external link part, you have macro over here. The only difference between this and the next file is right here, you need to use the production rules, BNF or context-free grammar, and your action is similar. You have a C statement or cobra, and usually this is the target code for your program. Because this is Bison, it will be used for the generation of intermediate code or the executable file code. And it's different from the Lex. Lex is trying to return the token, but right here is different. And it has the BNF format. We will show this how to write a BNF later. And the definition part, also you have a percentage sign bracket for inclusion of the C program. And then you have the YY definition. Yet definition. Yet definition, you have the percentage sign star. This is for the assignment for the starting production rule. For example, in the calculator case in the figure 2.16, this starting production rule should be the program rule. And percentage token, right here you define a token identity. And why we need to define a token identity right here in the .y file, the Bison file, instead of the Lex file? It's because that the Bison file or the yet file is used with -d to generate the token table. That would be the token table header file that would be fed into the Lex or Flex program. That's why this is needed. And also union and type are also way of specifying the token types. And let's move on. So the part 1 definition, we can define a token, that's integer token. And we can define the return, the data type, YY style as integer. And we can define this integer, we declare it as a token already. Then we define integer 258. 258 is the token index for integer. And we can include this YY style, YY value, YYS type, YYS type, that is actually defined as integer. And this external one because we are getting this from the lex.yy.c program. And let's move on. The middle section represents a grammar, a set of production rules. The left-hand side of the production is followed by a column. So the left-hand side, put a column behind it, and then you put your right-hand side over there. On the right-hand side, your rule will be separated by vertical bar. This is the OR. And then the action part will enter by the braces. And the end of the rule will be a semicolon. So right here is one example. You have the statement list, and then the right-hand side can be a statement or a statement with statement list. And your statement is defined as ID. This is one token plus sign, and then another ID. So this is actually A plus B or B plus C, something like that. And another statement is ID minus ID. So this actually is a very simple calculation. And this one will just print out statement, and this one print out plus, this one print out minus. So, and Bison value for declaration. And this will be part of the chapter 4, but we just try to discuss this briefly. So you can use $1, 2, 3, 4 to refer to the right-hand side symbols. And $, refer to the value for the left-hand side symbols. Every symbol has its value associated with it. So default will be the left-hand side equals the right-hand side's first value. And what this means is actually, for example, we have A plus B, then this $1 is for this first ID. You put a plus over there. This is the action function. Then you put the ID for the third. This number 3 is this ID. The plus sign is number 2, but it's of no value, but a operator. Then the sum of this will assign a value to the $, sign. Now it's for that term. And for this dual, this ID will minus this ID and assign a value to the term. So this is actually evaluating the syntax tree. So part 3 will contain various C code that support the language processing and simple table implementation, something like that. So let's finish this basic definition for the file structure. Now let's move on to this last lecture. I will show you a Bison file for simple calculator and to do simulation for it. So this is the second part for the Bison application. So we can use the Bison to generate a token definition to fit in the flex for generation of the YYLex. And you can define the digits or the numbers as the token type integer in your .y file. Remember, this is now, this one is actually in flex. So the integer type is defined in the parser, and the parser will put the integer type in the calculator.tab.h file for the inclusion in the flex file. And the current token, current matched string, now matching this will be a string, and the string will be converted to a YYL value, and that YYL value will be for future calculation in the parser part. So basically, we will store the value of the integer in YY value and return the token integer to YAG. That's Bison in our case. The type of YY value is determined by YYS type. And in this case, it's integer. The default type is integer. And token, we define the integer as the number 258 type, because 0 to 255 are reserved for character value to match the ASCII code. For example, if it is a minus or plus sign, we would just return the current YY text, the matched pattern. So for example, you see a token of the plus sign, the plus sign will be returned. That's what this means. And if you see a minus sign, the minus sign will be returned. Okay, so this is the next file for the calculator. Basically, we write down this part and then include this y.tab.h. This is the YAG format, and in Bison format, this should be calculator 1.tab.h. And right here, if you see a number, you return the integer type token and also convert the match string into integer value. And if you see a plus minus sign or \n, change line or plus minus, you just echo out the string. If it is a space or tab, you skip them. And any other character is illegal characters. So this is the tokenizer to generate a token and also generate a value from the token. And your program talking about the parser definition file. Internally, Yak maintains two steps in the memory: a parser stack, a value stack. So actually, this is similar to the LR parser. We will talk about this later. The parser stack contains terminal and non-terminal that represent the current parsing state. The value stack is an array of Week2S2 type element and associate a value with each element in the parse stack. For example, when Lex returns an integer token, Yak shift this token to the parse stack. At the same time, the corresponding YYL value is shipped to the value stack. Okay, we will show a figure that will be easier to understand. So right here is the one very simple calculator. Your program will define as a program with a expression, and then the change line sign is the end of the program. Or the program can have nothing because it's a bar, there's nothing there. That is also a program. You can have an empty program in our simple calculator language or a expression. And then if this expression can be one single integer, in that case, you will just return the value up to the tree for the expression, and we will show this what this dollar sign mean later. And then if you have the expression plus expression, you'll return this two expressions value to the upper level expression, and minus sign similarly. So basically, this is how to calculate the value for the nodes and the production rules. Okay, and the main program just call this YY pass. So YY pass will actually pass all the token. It will call the YYLex, and YYLex provide the token to here, and those tokens will be processed by this rule, and this set of rules will be actually converted to the nested case or switch functions, loops, I'm sorry. So now, and actually, your input string will be sent to the parser, and parser look at the table and push into the parse stack. And the parse stack will evaluate like tree like this. And the rule section resemble the BNF grammar. So basically, this expression column, expression plus expression. This actually is similar to expression and then go to sign and then ID or expression and then plus sign and then expression, but it's written in different format. But it's actually content-free grammar or BNF grammar. With lab recursion, this contains 0 or more expressions. So actually, apparently the program is not LL grammar. Otherwise, the LL parser won't work on this case. So Yak or Bison doesn't support the LL type grammar. So right here, you have parser, has semantic stack, and then you would actually call the Yak to provide a symbol, and symbol also come with the value, and the value being assigned to the this $1, $2 sign seen in the rule. So basically, from the token, you generate some integer. So integer assigned to this $1 or 3, and then they do calculation and push up. So this is what it is. The value being passed in and assigned to the dollar sign 1 and 3, and perform the action, and then return this dollar sign back to the stack, and for higher level operation. So right here, I won't repeat this. Let's look at this step. It's easier to understand. Say we have the expression plus expression 1 plus 3. The number 2 is a plus sign, right? And this is called the pass stack. So we push in the tokens or the expressions, terminal or non-terminal, into this pass stack. And in our value stack, we have the value associated with this that assigned to this dollar sign 1. That's called by the YYL values. And that actually associated with this. So these are 2 steps. When this push, it will push as well. So you push a token in this pass stack. At the same time, you push in 23 for dollar sign 1. And then when you push the plus sign, you also push in the dollar sign, plus sign over here. You push in the 3, you also push in this 31 in there. And then the whole thing sum up, you pop up this 3, you push in this dollar sign, and then this 54 also being pushed in. And this upper level expression may be adding with some other people, and then it will be pushed in and then pop up to higher level. So effectively this that stack operation with pass stack and the value stack will be summing up to the tree. Okay, then let's go for the program. And right here, we go to this CDEF. Now we go into this shift right mouse key. Shift right mouse key, open command line, and let's go into this Bison one. In Bison one, let's look at this. I'll try to use Notepad, then we can see more window. First, let's look at this .y file. Let's use Notepad. I'm sorry, this is not appropriate. I still use the break it. So this calculator 1.y actually is like this, and it will include a YYLS from the external .c file, and the duo is written down like this. It is exactly the same. It's exactly the same with the previous the listing on the program on the slides. And let's look at the YY on the calculator 1.l. This one will get the file calculator C1 calculator 1.tab.h file generated by the Bison file, and right here it will return the value of the match integer into YY value, and YY value assigned to the $1 and 3 in that case. So okay, this is it. Now let's do this. First, let's do Bison-D. We need to have the -d to generate the table. Then we use calculator 1.y. Okay, that's okay. That doesn't create a problem. It said that it will perform for shift and reduce functions. And then the next thing we would do, right now, actually, we already create the .h file. So right now, the next thing we would do is do flex and then calculator 1.l, and then it is done. Now the next step would be GCC, and then at this time you will have the calculator 1.tab.c. Another file is the max.yy.c. Then you dash O, and then you create calculator 1 program. Okay, then the executable file calculator 1 will be created. Then let's run calculator 1, and without any input. Click. Okay, there's nothing. Then we type in 3 plus 7. Click. You got 10. So actually, this is one interpreter. So let's do 9 minus 3, 6. Let's do 14 minus 8. Let's do 100 plus 89. So this is one interpreter. So when we want to get out, I write down one extra, let me show you. In the .l file, I write down one more regular expression to exit the program. So this is actually a interpreter, and I type exit, you get out, the program is done. So this is the function for this calculator 1. Very simple calculator. Later we will have more complicated, the version that is used in our textbook. But now let's look at something else. Let's open this BO2. This BO2 program is a Windows script. It starts with IEM. IEM means command line. So the first line is totally useless. So you do Bison-D calculation 1, calculator 1.y. That is matching this statement. And then this command over here. And then you have a flex calculator 1.l. That's doing this. And then GCC stuff is this. So actually this BO1 is a batch file. I'm sorry, BO2.bat is a batch file. So actually that's wrong. That's wrong. So this is actually a batch, a batch file. We click BO2, and you finish whole building for this calculator 1 project. Okay, but this is done in Bison format. Let me open this BO1. Let's open this BO1 with bracket editor. Same thing. We start with the REM for the command line. Then we have Bison-Y space -d. The -y means YAC format. So this Bison working in emulator for YAC. And then we take in flex calculator 1.l, and then GCC-cy.tab.c. So the difference is, using this BO1, you will actually create this y.tab.c instead of the Bison one, calculator 1.tab.c. And then the table file, the same thing, you have the y.tab.h instead of calculator 1.tab.h generated by the Bison format. And this one, y.something is generated by the Bison, the YAC format. And then you use GCC without assigning the -o option. You actually create the object file y.tab.o and the next.yy.o, and then you use GCC again -O to the calculator file. So now let's run this BO1. Same thing, then we do calculator 1. We can still do 90 minus 74, something like that, and then we get out of there. So basically, we have BO1 batch file for EX format and BO2 file for the Bison format. And today I will end here. Let me check our friend, are they still awake? Hello. Okay. Any question? Okay, great. I hope you guys can download this file and then practice yourself. Then you will pick up the idea of parser, and actually the Bison one is very valuable. You will know how a very simple interpreter is constructed. And you know Python is a interpreter-based program. And we have this Bison program that can help us to generate a compiler, and also it can also be used to generate an interpreter. And you know this type of interpreter or compiler, sometimes you can incorporate the module into your bigger program. That would be very useful. For example, right here, we are trying to do www, but whatever here, right? This one actually has a hidden interpreter over there, single line interpreter over there. Anything you type somewhere has that hidden interpreter. And I believe different language probably have similar LEC or EX format. Maybe they are Java version, they are Python version. There are people doing the open source file program for everybody. And right here, let's study the C version because it's the most traditional EX and LEC format. And it will be useful, and later you can find the type of program you need in your own program to build a bigger project. So we have the regular expression that can be used when you have the input file to check a single input string, whether it's valid or not. And then we have the then we have the flex. You can use that as a standalone stuff to generate a token, and that token can be you can think about a token is a pattern matching or a classification tool, and you use that classification tool, you can fetch a certain proper function to process on it. And the last one, we use Bison or Bison with the flex to generate a certain compiler or interpreter that can build in to process your string or input string or comments. That's the purpose for us to study these things. And in the next few lecture, maybe tomorrow, I actually need to finish the chapter 2. We will be on the LL parsing, LR parsing, and then we will wrap up the chapter. Okay, thank you. Bye.